Hello everyone. Good morning students. Hello.
Good morning, sir.
Good morning. So I will start with my lecture now. Sometime back I started with a second chapter on the magnetic field produced by magnetic materials. The magnetic materials are the materials that can be magnetized. The magnetic materials all the time I used to give the three examples because there are three different types: iron, copper, and aluminum. Normally, any magnetic material does not produce any magnetic field because it is not magnetized. It is not magnetized because the magnetic moment of different atoms of that material, different atom means electrons which are orbiting around the nucleus, so that produces the magnetic moment. And magnetic moment being a vector quantity, the total resultant magnetic moment of all these orbiting electron, that is atomic current, is zero. So the material is not magnetized and it does not produce the magnetic field. So there are two physical quantities here. One is a magnetization, other is a magnetic field produced by that magnetic material. Then a given material gets magnetized in response to the external field. Example, you can take the magnetic material near the bar magnet, then what will happen is it will produce the magnetic field, so it will get magnetized. Or you can keep that inside the solenoid, then again it will get magnetized, it will produce the magnetic field. Now that external agency which is responsible to produce the magnetization of the material is called as a magnetic intensity H. So three basic physical quantities in the magnetic material are magnetization, capital M, magnetic induction, capital B, and magnetic intensity, capital H. All these are a vector quantity. Now next, we'll see the different types of the magnetic materials. Magnetic material means the materials that can be magnetized. Now this is the magnetic material, they are a medium. Media means a plural, medium is a single. Now first thing is, in the electrostatic, we have a dielectric medium. So these terms we have already defined: isotropic, linear, non-linear. Now isotropic means all the physical quantities means different physical quantities. It can be magnetization, magnetic intensity, magnetic induction. They have the same direction. Same direction. Then the linear medium means this physical quantity, different physical quantities, H, M, B, they are linearly related. Linear, y equal to mx plus c, linearly related, or y equal to mx. So y is proportional to x. So each physical quantity is proportional to other physical quantity. So that is a linear medium. Then we have a non-linear medium. In non-linear medium, these physical quantities are not linearly related. That means they are not directly proportional. Now first we will consider a linear medium. Means physical quantities are directly proportional. Example, the physical quantities are vector m, vector h, and vector b. Now, vector m is directly proportional to vector h. So, if h is something to do with the external field, because of the external field, the material will get magnetized, and this magnetization is proportional to magnetic intensity. So as the external intensity increases, that means external magnetic field increases, the magnetization of the material increases, and it increases the linearly. They are directly proportional. The constant of proportionality, that is called as a magnetic susceptibility. Similar thing you have seen in the electrostatics. There it was a polarization. See, there is a polarization. So vector P was there. Then there was something called the vector D, displacement vector. So that is in electrostatics. So now here similar quantities are there, magnetization and the magnetic intensity. Since they are directly proportional, magnetization is proportional to the magnetic intensity. Now magnetic intensity is because of the external source. The constant of proportionality, that is called as the magnetic susceptibility. Now, depending upon the sign of this magnetic susceptibility, whether it is a positive or negative, the magnetic materials are classified into two. If this sign of this susceptibility is negative, see, negative means the magnetization is opposite to the external intensity. So you are applying the field in one direction, then material get magnetized in opposite direction. So total resultant magnetic moment is produced in the opposite direction. So that means the susceptibility is negative. So magnetization is opposite to that of the magnetic intensity. Then that material is called as a diamagnetic material. Diamagnetic material. The property is called as a diamagnetism. Now this diamagnetic material, if you take it near the magnet, it will get repelled. But what happens is this constant of proportionality has a very small value. So magnetization is very small as compared to the external field. That means what will happen is if you take the magnetic material near the bar magnet, see bar magnet produces non-uniform magnetic field, then what will happen is it will get weakly repelled. Example is a copper. Normally, in normal circumstances, we don't see that repulsion because that the repulsion is very weak. But if you take the copper near very strong magnet, you will find that it is slowly repelling. Now, if you keep this magnetic material like a copper, this diamagnetic material in the uniform external field, then what happens is inside the field becomes less than the outside. Suppose you take a uniform field and keep it inside this diamagnetic material like copper, then what is founded, the inside the field become less than outside. So we say that magnetic induction is weakened by presence of this material. So these are the diamagnetic material. Then the susceptibility is positive. Positive means what? Direction of magnetization is same as that of the magnetic intensity. So the resultant magnetic moment is the same direction as that of the external field. Then that material is a paramagnetic. It is called the paramagnetic, and the property is called as a paramagnetism. So if it and again the value of this susceptibility is very small. So magnetization is very small as compared to the external field. And if you take this type of paramagnetic material near a bar magnet, you'll find that it is weakly attracting. The attraction is very weak. It is weakly attracted. Attraction is very weak because that value of the susceptibility is very less. If you keep this magnetic material inside the external field, then what you will find is inside the field is more than the outside because the magnetization is in same direction as that of the magnetic intensity. And this susceptibility depends upon the temperature. For both this material, it depends upon the temperature. So these are the classification of magnetic material based on this sign of the magnetic susceptibility. Then, as I mentioned that we are considered the linear magnetic material. See, this paramagnetic material and diamagnetic material, they are linear material. Linear material means the physical quantities are linearly dependent. In more particular, physical quantities are directly proportional to each other. So, if the magnetic induction is proportional to the magnetic induction, so what will happen is, as external field increases, so H increases, the magnetization of the material will increase, and hence it will produce more and more magnetic field around it. The constant of proportionality is called as the permeability. It is similar to the this uh, permittivity in case of the electrostatic. So it is called the permeability. is a constant quantity. For dimagnetic and paramagnetic, permeability is a constant, susceptibility is constant because it's a constant of proportionality. Now, this equation we have already derived or we have stated earlier. The relation between magnetic intensity, magnetic induction and magnetization of the material. Now, if you substitute here B, mu H, then M here, that chi H. And when you simplify this, when you see H will cancel, this H will cancel. And if you simplify, you will get mu equal to mu naught 1 plus chi M. Chi is a susceptibility, the Greek symbol. And mu naught is the permeability of the free space. Mu equal to mu naught 1 plus chi M. And the ratio of this mu by mu naught, permeability of the medium divided by permeability of the vacuum. Mu naught is of the vacuum. Permeability of the given magnetic material to the permeability of the free space. That ratio is called as a relative permeability. It is similar to relative permittivity in the electrostatics. But in the electrostatics, there is a special name for that, and that is called as a dielectric constant. So in this case, there is no special case for that, because normally this relative permeability, this concept is not much used in the magnetism. But in the electrostatic, it is very much used. Everywhere you require it, dielectric constant. Here it is not much of use. So it is not given a separate name. So this is about the dimagnetic and paramagnetic material. More detail of that, we'll study that in the next chapter. Afterwards, we'll study in detail why such thing happening in dimagnetic material and paramagnetic material. Now what happens is, you take a dimagnetic material, copper, paramagnetic material is the aluminum. See, aluminum will be weakly attracted by the bar magnet. But we don't observe. If you take a bar magnet near the aluminum vessel, it doesn't get attracted because attraction is very weak. But if you take a very strong magnet, then it will get attracted. But what happens is, if you take out this material out of the field, you take out the copper or aluminum, dimagnetic material or paramagnetic material out of the field, then what will happen is, again it will get demagnetized. So it will magnetization will become 0. So as long as it is in the magnetic field, it is magnetized. The magnetic material magnetized in the direction opposite to the external field, and paramagnetic material is magnetized in the direction of the magnetic field. But if you take it out, the magnetization becomes 0, and the magnetic induction will not be produced by this material. Now there is a third category of the magnetic material called as a ferromagnetic material. The property is called as a ferromagnetism. Now what happens is, this type of material, when you keep it in external field, they will get strongly magnetized, very strongly magnetized. So magnetization is very strong because the susceptibility of that is very large. Susceptibility, permeability is very large, and it will get strongly magnetized. And if you take it out, it will not get demagnetized completely. It retains the magnetic property. So this type of material are used to make a permanent magnet. The permanent magnets are made from the ferromagnetic material. So in the magnetic field, they will get magnetized and it will get strongly magnetized. And if you take it out, that part of that magnetism is retained. So magnetism is never lost. It will just like you take a iron pin, take it near the bar magnet, you remove it from the bar magnet, and if you put it back into the box of the pin, then you will find that pin will attract the other pins. That means it is, when it is brought in contact with the bar magnet, it got magnetized, and when it taken away from the bar magnet, that magnetism has been retained. So the permanent magnet or permanent magnetization is there only for this ferromagnetic material and not the dimagnetic material and paramagnetic material. But a difference between this and the dimagnetic paramagnetic is, it is not linear. It is not linear. That means the magnetization is not directly proportional to the magnetic intensity, or the magnetic induction is not directly proportional to the magnetic intensity. If you plot a graph, you will not get a straight line because it is not a linear, which means that So constant of proportionality will not be there. So this constant will be variable. See, that means that chi, that susceptibility and mu permeability, they are not constant. They are variable. So that is the property of this ferromagnetic material. Now, if you plot a graph of magnet, say suppose you take a solenoid like this, you pass a current, and keep it inside the ferromagnetic material. This is a ferromagnetic material. See, this material is a ferromagnetic material. You keep it inside. Then, starting, see, uh, I already mentioned last time that this H can be written as N into I. N into I. N is the number of turns per unit length of the solenoid. I is the current. For especially for the if it is a solenoid, normally we magnetize the material by using a solenoid by passing a current. N into I. N is the number of turns per unit length. So I is the current. So it entirely depends upon the external source. So that's why H is something different physical quantity, which is everything is external for that. So if current is zero, external intensity is zero, so magnetization will be zero, magnetic field will be zero, produced by the solenoid. As I increases, H will increase. So what you do is you increase the current. So increase the current, then H increases. See, H increases, and you find the magnetic field produced by this material, magnetic field. And if you plot a graph, you'll find that you'll not get a straight line, you'll get a curve like this. It is not linear. See, if you try to find the slope at each and every point, the value of that slope will be different. That means mu will be different. B equal to mu h. See, B equal to mu h. So, if you try to find the slope at each and every point, then you'll find that value of mu will be different. So, this is not a linear material. So, what happens is this will increase non-linearly, and afterwards that B will remain constant. B remains constant means the magnetic field remains constant. That means the magnetization does not increase. Magnetization remains constant. So if you keep this material inside the external field, then at a certain value of external current, at a certain value of the H, the magnetization of the this it does not increase further. That means what happens is all the magnetic moment of this material is aligned in the direction of external field. So more no see, since all have aligned, so no more alienation is possible. So that's why it remains constant. This is called as the saturation magnetization. It is called as the saturation magnetization. Maximum value of that magnetization corresponding to this B, the material will have some magnetization, and you can find it using this formula. By using this formula, you can find it that M will remain constant. That is called as the saturation magnetization of the material. And if you try to plot this relativity against H, then it will increase, becomes peak, and then decreases. And if you apply your calculus, you will find that peak is when the magnetization has attained the constant. You will find this peak. The magnetization has attained the constant value. The next is this ferromagnetic material. They show the certain property called as a hysteresis. So now what you have to do is, again, as you have done earlier, take the ferromagnetic material. So example of ferromagnetic material is iron. Another example is nickel. These are all ferromagnetic material. You keep it inside that solenoid, and starting with I equal to 0, that means H equal to 0, find out B and plot a graph of B against H. And you will find that the increase in B, that means magnetization, B corresponds to certain magnetization, is not linear. And afterwards, as we have seen earlier, it remains constant. Magnetic induction produced by the material is constant, so magnetization is constant. So this is when you are increasing this H. Now if you decrease this H, you will find that up to that saturation magnetization, it remains constant. But if you decrease it, it does not trace back its original path. Say, what happens is, when you increase H and when you decrease H, the path followed is not same, path followed is different. And path follows is different. That means what happens is, here see, when H is 0, I equal to 0. Still, it produces the magnetic field. That means still that material has a magnetization. Now this point of magnetic induction, where H is 0, that means external field is 0, is called as a retentivity. That means it is just like taking out that material from the magnetic field. See, I has become 0, that means H has become 0. External field is become 0. At it produces a magnetic induction. That means there is some magnetization. So this value of the magnetic induction is called as a retentivity. So it is able to retain that magnetic field. So it will not become completely 0. So it will still produce the magnetic induction, although the external field is 0. Then here this H is negative. That means you apply the field. That means you through the solenoid you reverse the direction of current. Reverse the direction of current. When you reverse the direction of current, direction of intensity will get reversed. So direction of external field will get reversed, and you will find that the magnetic induction become less and less. That means magnetization become less and less. That means it is getting demagnetized, and you will find that at some value of the external field, the magnetic induction produced by the material becomes 0. That means the magnetization becomes 0. That means that material is completely demagnetized, and that is called as a coercivity. Coercivity. So coerce means to oppose. So what happens is, from here to here, it was opposing the demagnetization. So finally, at this point, it has become demagnetized, and that point, the value of that H is called as a coercivity, or this point is called as a coercivity. Then again, if you make it more and more negative, you will find like this, increases there. Then again, when you increase the value of the H, then again you'll find that it is varying. But you'll find that every time when it is increasing or when it is decreasing, the path followed is different. Path followed is different. So this path followed is different, and that means what I mean, see, the path where the point where it completely demagnetized is found beyond this point, beyond this point. So this phenomena is called as hysteresis. In the German language, hysteresis means to lag behind. And the phenomena of hysteresis is very important for the this ferromagnetic material. Now, one can show that, and we will show it in the later chapter, that if you find the area of this loop, then what happens is you are magnetizing and demagnetizing. Again magnetizing. So you are magnetizing, demagnetizing, again you are magnetizing. So one path is complete. One cycle is complete. You are magnetizing to the saturation value, again you demagnetize it, and again you magnetize it to the saturation value. So path is complete. Now in this one complete path, if you find the area of this curve, is proportional to the energy lost by that magnetic material. What happens is, if you magnetize and demagnetize, you will find that that material becomes heated. Heat will be produced. So this energy, electrical energy, which you are using from that solenoid, is converted in form of the heat. So there's a power loss is there. That loss of power is proportional to the area of this loop. And again, we'll prove about this area of this loop. And what happens is, many times this type of the ferromagnetic material is used in some devices you might have already studied earlier. We'll study that detail later on, like the transformers, then motors, dynamos. This type of ferromagnetic material is used. And what happens is, these transformers, motors, it works on the AC. Now in AC, what happens is, the current increases, decreases. It follows in one direction, then in opposite direction repeatedly. So there is a magnetization and demagnetization of this material, and energy is lost. So one who design this transformer or a motors, they have to take into account this loss. They should see that loss is as small as possible. There are also eddy currents, so loss should be as small as possible. Now, to reduce the loss, what is to be done is you should take that material where this area of the loop is as small as possible. Example, a soft iron. Soft iron is also called as a wrought iron or soft iron. Among all the material, it has a least area of this hysteresis loop. That means it will produce minimum amount of the power loss. So this, from that point of view, this hysteresis loop is very important. Then see the ferromagnetic materials, they are used to increase the magnetic flux in the current circuit. Magnetic flux. You might have seen in case of the moving coil galvanometer or ballistic galvanometer. So what is done? A winding is there. What is important is the winding in the external field, winding in the external field. Now what happens? What is done is that winding is done on a cylinder like this, a soft iron core. That winding is done. Winding of that wire is done on this core. And you studied the ballistic galvanometer for practicals. You might have studied moving coil galvanometer in the 12th standard, and you'll find that it was mentioned that the winding is done on the soft iron core. Soft iron core is a ferromagnetic material, and this winding is done actually without this soft iron core also you can do the winding, but yet it is done over this soft iron core because soft iron core is a magnetic material, ferromagnetic material, and what happens is the soft iron core, its permeability is very large, so it will produce large amount of the field inside. So field inside will increase, so magnetic flux will increase. So that is that first use, to increase the magnetic flux of the current circuit. Then this ferromagnetic material is used as a source of magnetic field. That means to make a permanent magnet. So then make a and there's a process for that. And normally what happened is in olden days the soft that permanent magnet was made by keeping it near the another bar magnet for a very long time, but that was not convenient. So today what is done is the solenoid is taken. See, solenoid is taken, and inside, suppose you take a iron piece or nickel piece or cobalt piece. These are the ferromagnetic material. It is kept inside, and what is done is a large current is passed. Very large current is passed. That means it is subjected to large magnetic field. And then what happens is when you switch out of this, so this material will get permanently magnetized. So what happens is when you are switching it off, there is a problem there. When you switch it off, as we have seen here, there is a demagnetization. So what is to be done is it should not be completely demagnetized. So that's why what happens is that this region is also important. We have to see that you have to switch it off in a certain way so that the demagnetization is as small as possible. So as large amount of magnetic field is retained by that material. So second quadrant, this is second quadrant is also important. So when the manufacturer makes this a permanent magnet by using the solenoid, then they switch off in a certain way so that the demagnetization of that material is as small as possible. Okay, so that's why the second quadrant is also important. So with this, uh, uh, I'll hold here lecture. Now I'll take your lecture day after tomorrow, and not tomorrow. Day after tomorrow at the same time. So next lecture will be taken day after tomorrow. That is on the Thursday at the same time. Thank you very much.
Thank you, sir.
Okay, welcome.
Thank you, sir.
All right.